So now I'm going to show you how to input the data into Pvgis so that it plots what you want or need, in better case need. So let's jump right into that. First thing, you enter the address. If you don't enter the exact address, you can actually pin the point in the map. Then there's actually an option to input the O and L, so opacity and legend. Could alter the results a little bit. You can also input terrain shadows, and now it lets you choose what kind of solar production it is. So either it's grid connected or off grid, or it lets you plot monthly, daily, or hourly data. So in this case, the off-grid calculation is not going to be of use to us, because if you combine multiple planes, it cannot really, it doesn't let you enter those. What we can use is the grid connected one, or then we can plot individual data for each month, or hourly data, which is going to be very interesting to look at. However, at this point, I'm going to select grid connected. It asks you which kind of database to use. It lets you input the peak power, and now we're selecting, we're putting the peak power of an individual plane, and it's 13 kilowatt peak. It also accounts for system loss, which is 14%. I'm gonna leave that, although it could be a little lower. However, this is pretty much gonna calculate the worst case scenario. And now freestanding, different case. For us, it's a roof added PV with a slope of 48 degrees, and the azimuth of the southwest plane is 16 degrees. What's interesting, the Pvgis can actually optimize the slope and the azimuth if you're in the design phase of the building or are planning a different type of PV array. It can actually calculate the most optimal slope and azimuth for you, which is interesting. And you can also enter the electricity price and the PV system cost, which will then automatically calculate the interest for you. However, if you're combining multiple planes, again, you will need to do it on your own in Excel. So, with that being said, I'm now gonna click Visualize Results. And this is what it outputs. It outputs basically the monthly energy production, at least the theoretical one, for that plane. As you can see, as expected, lowest value is going to be December 419, yes. And the highest value is going to be in July, 1.5 megawatt hour, pretty much. Those values are really nice. Provided that, yeah, what we can actually have a look at is actually balance this data with the actual energy consumption of the system. And so if we're planning a fully autonomous system, this is after the load profile and the battery capacity that is enough to run for like 5 days. This will be the second condition to meet, so that in every single month it produces enough electricity to cover the consumption. So we're gonna have a look at whether that's true or not with this one individual plane. What we can do later, if it doesn't work, is we can actually cover more planes and see if the sum is gonna cover the consumption. So stay tuned. In order to quickly calculate the potential of a given plane, you just simply input 1 to the installed peak power, which makes it a constant, and then you make two results for the planes you want to compare. In this case, both are going to have the azimuth one of minus 167, and one of them is going to have the slope of 20 degrees, the other 48. And I already did that, and I found out that actually the slope 20 degrees is more beneficial in Northeast in my location than the 48. So you are looking for the yearly PV production basically. And based on that, you can then draw another panel layout for the 20-degree plane and then find out whether in sum it makes enough energy in the months you're looking for. All right, so now that I have laid the panels out on the roof plane, I did one additional step, and that was that I actually made a quasi wiring diagram, which is going to be very helpful for those who are going to be installing the panels. And that is because we also need to think of dividing the panels into individual MPPTs or into individual strings. And so I'm going to illustrate what my thought process was here. And so the determining factor when actually dividing it into MPPTs is, for one, if you've got an area of the roof plane which is perhaps shaded by an object, a building or trees, this really should be a separate string. And the second determining factor is pretty much the parameters of that MPPT, which I'm going to show you later how to check. There is a great Excel on that. And so what I did here, this design was a little tricky because it's not symmetric and there are 26 panels. So I found out that the MPPT is gonna handle like pretty much 8-9 panels at most. And so what I did, I divided it into 3 MPPTs. First of which is gonna be this area right here. So those panels and those panels, and then 2 pretty much symmetric MPPTs, MPPT2 here, and 3 as follows. And now I put the panels into strings, and for the first one it's going to be strings of 4. So 2 strings of 4 that are going to be parallel, connected parallelly to each other, as you can see. Here I did a little trick, and you might have found out that these 2 panels are actually reversed, meaning that their polarity is going to be different than all the other panels, so that the sequence in a string gets the polarity from plus minus plus minus plus minus and so forth. And this pretty much saves some additional wiring that would have to occur if it were laid out as normal. So it's just a string running from here, basically. This is another string, and those are going to be connected parallel. And now for the other 2 MPPTs, there are 3 parallel strings of 3 panels, right? So 1, 2, and 3. And the same goes for the MPPT3. Why I did that is because you can actually then later check in the Excel whether the MPPT is capable of handling those. And you might be also asking the question whether it's okay if we've got, there's going to be probably different voltage on the 4 string versus the 3 string. And in this case, it's okay because it runs on a different MPPT. And provided that the MPPT is okay with those and okay with those, it's going to be fine. Okay with those. Fine. So in the wiring, each panel has 2 MC4 connectors, male and female, and to connect them parallelly, we're gonna use these kind of like couplers. And what we're gonna end up in the previous ventilation shaft, now it's gonna be the tile through which we're gonna run the cables, we're gonna end up with a total of 3 negative 6 square millimeter cables and 3 positive 6 square millimeter cables, 2 of which, positive and negative, running to each MPPT. And that is going to be our design. So this is almost a fully covered plane. I don't think one could fit more panels of this size. Maybe one could fit one here, but that's not the case here. Okay, so this is the logic behind putting the panels into strings. It's very simple. Just note that in series, the voltage adds up, and in parallel, the voltage stays the same, but the sum of the current adds up. So with that, let's leave this thing and focus on the Excel. I was almost in the middle of making my own Excel, but then I found out that there is one that is much more detailed and actually has the MPPTs from Victron. And now you might say this is Victron specific, but in reality, it's very nicely tied together, and you can actually input any other module, so any other solar panel, or even any other MPPT, provided that you know the values here in their based on their technical sheet. And so what I'm gonna do is I'm gonna actually input my own panel, which is different because I will be using a Swiss Solar panel, which is right here. And so I'm gonna show you where to get the values. Now, we can use the slot here for custom panel. So let's call it Swiss panel. I'm not gonna input the type. It has 500 watts, so 500 watt peak. And now where to get these values, right? So you are looking for the standard test conditions now, which are pretty much for the irradiance of 1000 watts per square meter, 25 degrees module temperature, and air mass 1.5. And so you're gonna just simply input the values here. For this model, it's gonna be 4062 volt. The current is gonna be 1231. And VOC, we're gonna use this value, 4883. For the ISC, it's gonna be 1320. And there's also a temperature coefficient for the voltage and for the current. So let's see, we got temperature coefficients here, and they're given in percent per degree or percent per Kelvin. So we're gonna just simply use the VOC minus 0.28 here, and for the current, it's gonna be 0.05. Great. So that's for the panel. Now let's have a look at the MPPTs. Not this one, these ones. So there are basically two model rows, let's say. So either they're the Blue Smart Solar, or Victron also has the RS, which are basically more powerful, and then they allow you to connect multiple strings. And so now in this case, we could use one of the RS modules, or we could use multiple of these, I believe they're gonna be. We're gonna see whether that fits. In reality, using 3 of these is gonna be cheaper than one of the RS modules. So let's see. For calculating the blue solars, we need to input our module, which is going to be the Swiss panel. And now, according to the panel layout, there are basically there are 2 scenarios, one of which has 3 series and 3 parallels. So 3 parallel series of 3. And we should be using the 200, 48 volt, that's correct. It also takes into account the cable length and cross-section. Now at this point I haven't yet calculated the cable lengths, but it should have no significant effect. And the cross-section is going to be 6. We can later also check another method of well, but this is Excel actually does it for us, so that's nice. And what it actually checks are things like max input voltage, so that's fine, 250, because actually with the decreasing temperature, the voltage tends to be higher. So you can see that that it's 160 volt for the minimal temperature and 101 volt for the max temperature. It also checks the current, and it also checks the current at maximum temperature, which is going to be a little bit lower because, well, physics. And what is important for us is we should be checking this box, which alters the temperatures. And now we can see that this particular MPPT is going to be fine with these 3x3 panels, but it limits the power. The power is limited by the low temperature. And that is simply because, well, it's higher than the value there. What we need to check as well is the other case scenario for the bigger MPPT. So we'll do that now. Let me just open up the best possible software to make panel layouts in. Wait a minute. Oh yeah. So here we get the panel layout. And as you can see, we did the case with the MPPT 2 or 3. They're the same. So 3 series and 3 times parallel. And now we're gonna do the MPPT 1, which actually has 2 strings in series of 4 panels. So let's input that right now into Excel, please. So 4 panels in series and 2 in parallel. And as you can see, that's all fine. The potential here might be for a lower, for a different module, let's say. So we're going to try the 85. This one is limited, so it could work with this one. However, the 250, 100 is probably going to be better. And you can see that this one is already limited in 2 of the conditions. So, yes, this is pretty much what we wanted to check. And we found out that for the 3x3 array, it's going to be slightly limited, but that shouldn't be of any issue. It's just going to limit the power. The other variant would be to use one of the RS, but that's a slightly more that's a slightly more expensive variant, as I said. So this is how you check the compatibility of the panels with the MPPTs. This Excel is brilliant, and I'm so thankful that, that someone has made it. All right.